Okay, so a couple of the problems from section 3.3. Let's just kind of get things going. Okay, so, and again, if you've already done these, great. Okay, you can tune me out for a few minutes. Okay, so for problem 1, okay, so this is, we're trying to prove that this is an isomorphism. So we've got a mapping F from S to R. And R is the set of positive real numbers, and it's got this funky addition and funky multiplication that's defined in the problem. And then S is just the set of ordinary real numbers with the ordinary real number addition and multiplication. Okay, and so we want to prove that this is an isomorphism. Okay, so we've got to show 3 things. We've got to show, first off, that it's a homomorphism. Secondly, that it's injective. And third, that it's a surjective function. Okay, so we need to show that F is a homomorphism. And so this means we need to show that it preserves addition and preserves multiplication. So these 2 properties, RH1 and RH2. Okay, so if we look at RH1, so this is the preservation of addition property. Just a second. Okay, so if you just showed up, I'm going over a few of the homework problems, the ones that are due on Thursday, just to get you started on them, okay? And again, if you've already started them, great, okay? Just, you can continue working on some of the other problems. Okay, so this is section 3.3, this is problem 1. So we're looking at this mapping F, which maps from S to R, okay? And S is the set of real numbers with the ordinary addition and multiplication. R is the set of positive real numbers with this funky addition and multiplication that's defined in the problem, okay? So this was one of the homework problems from the previous assignment, okay, showing that this is a ring, or at least verifying some of the axioms of it. Okay, so for this we want to show, so for the preservation of addition property, we need to show for all A and B, I want to do this, yeah, A and B and S, okay, so F of A plus B is equal to F of A plus F of B. Okay, and now when you're looking at these 2 properties, RH1 and RH2, you have to make sure you keep in mind where the elements live. Okay, so A and B live in the set S. That's the domain of our function. Okay, and so this is the addition in S. And then F maps S into R, so our codomain is R. So F of A and F of B both live in R. So this is going to be our operation in R. And in R, we're actually using that circle notation. So this is going to be circle plus here. Okay, that's not very clear, but let me try to redraw it. Okay, and one of the things you want to do with these problems is you want to make sure you keep the notation straight, because if you just kind of ignore the notation and you just use ordinary plus for everything, you know, there's a very good chance that you're going to mess things up somewhere. Okay, so to prove this, well, this is straightforward. I'm not going to go through it, okay, but I just wanted to get you started on it. So you're going to suppose that A and B are arbitrary elements of S. That means just ordinary real numbers. And then you need to verify the equality. So it's just a matter of plugging in using the formula for the function on the left side and plugging in on the right side and just verifying that you get the same thing. And then for RH2, the preservation of multiplication, okay, it's going to be similar. Okay, again, on the left-hand side, these are elements in S, so this is going to be the multiplication in S. So that's just ordinary real number multiplication. But on the right-hand side, these guys live in R, so this is going to be the circle dot notation, okay, or circle dot multiplication. Okay, so again, you have to make sure that you keep your operations straight. Okay, so this is verifying that F is a homomorphism. Then you need to show that F is injective. So for injective, this is going to be for all A, B, and S. The definition of injective is going to say F of A equals F of B implies A equal B. Okay, so that's just the definition, or at least the contrapositive of the definition. So to prove this now, you're going to suppose A and B are arbitrary elements of S. Suppose the hypothesis and then you need to show the conclusion that A is equal to B. Okay, so you're supposing the hypothesis, namely that F of A equals F of B, so you can just write out what F of A is, what F of B is, and then from that you want to derive the conclusion that A is equal to B. And really the only mistake that you can make on this is, and this is kind of a common mistake, is people going backwards. People sort of starting with this conclusion and then deriving the hypothesis instead. So, you know, as long as you avoid doing that, it's relatively straightforward. Okay, so that's injective. And then finally, we have to show that F is surjective. So surjective, so this is going to be, according to the definition, this is going to be for all R in R, there exists an A in S such that F of A is equal to R. Okay, and what you have to make sure that you keep straight here is don't mix up your domain and codomain. So this is the codomain, that's the R. This is going to be the domain, that's the S. So to prove this, you're going to suppose that R is an arbitrary element of R. And then you need to find an A in S for which F of A equals R. Okay. And the way you're going to do that is you're just going to use the formula here. You've got an equation here, and you're going to solve that for A in terms of R. So you just want to solve this for A in terms of R. And then you also need to verify that it belongs to the domain. So this A has to belong to the set S, and it's got to satisfy the propositional function here. And so you should go through and verify it. And so this is where, in the examples in the videos, this is where I was setting up the two columns, doing an existence proof. So if you took 280 from me, you know that's how I do existential proofs, okay? Okay, so this is problem 1, okay? And so again, if you've already finished it, that's great, okay? But I just wanted to make sure that sort of everybody sort of was able to do this, okay? Was able to get going on it. Okay, any questions? You know, if there's anything, just holler. Okay, so now number 2. So this is, we've got G goes from R to S, and F goes from S to T. So we have 2 homomorphisms, okay? And so the picture here, you know, this is where we've got 3 sets, R, S, and T. And so G is mapping things from R to S. And then F is mapping things from S to T. And then the composition now, so the composition is going to be this function here. So this is going to be F composed with G. Okay, so F composed with G is going to go directly from R to T. Okay, and you want to show that this is a homomorphism. Okay, and so you need to show that F composed with G satisfies our two homomorphism properties. So that's RH1 and RH2. And so for RH1, what you're looking at is this is going to be for all. So now the domain for F composed with G is R. So this is going to be elements in R. So we can say A and B in R. And then F composed with G of A plus B has got to be equal to F composed with G of A plus F composed with G of B. Okay. And so this is going to be the preservation of addition property that you need to verify. So you're supposing A and B are arbitrary elements of R, and then you have to prove this equality. And what you're going to use is the fact that both F and G are homomorphisms. So each of those preserve addition. And now you want to, again, keep in mind where your addition lives, or where the elements live, and where what addition you're using at any given moment. So A and B both live in R, so A plus B is going to be the addition in R, okay? And over here, these elements are in T, so this is going to be the addition in T. Okay, and then after you apply G to A plus B, well, G is going to map the elements in R into the elements in S, and so you're going to have the addition in S. So you're going to end up using all three of the additions, okay, when you go through the verification here. And then the verification for RH2 is going to be similar, okay? Okay, 3. Let's take a look at this, okay? And so this is, we've got this set K is equal to R is in R, such that F of R is equal to 0 sub S. Okay? So this might look a little bit familiar if you've had linear algebra. This is actually the kernel of the mapping. Okay, but we don't usually call it the kernel when we're dealing with rings, but it's really equivalent to the kernel. Okay, let's see. I should look at the chat here, I guess. Okay. Okay, so this is, you want to show that K is a subring of S. Okay, so you need to show, okay, now when you're applying that one theorem in section 3.2 to show that a subset is a subring, you have to verify that it satisfies those two properties, SR1 and SR2. That's the closure under subtraction and closure under multiplication. But there's actually one other property that you have to verify that's usually kind of obvious, and so we sometimes ignore it, but it's to show that the set is non-empty. So you need to show that K is non-empty. And then you have to show that SR1 and SR2 both hold. And SR1 is closure under subtraction. And SR2 is closure under multiplication. Now, I know on the homework, some people were applying the theorem or trying to apply the theorem, but instead of using closure under subtraction, they were sort of reading it as closure under addition. And that's not the same. Okay, so verifying closure under addition is not the same as showing closure under subtraction. And if you only verify closure under addition and closure under multiplication, that's not equivalent to showing these two properties here. Okay, you can actually have sets that are closed under addition and closed under multiplication that are not subrings. Okay, but if you have these two properties, according to the theorem in section 3.2, this is going to tell you that this is a subring, okay? And so let's just take a look at, so SR1, okay, this closure under subtraction. So this is going to be for all, let's see now, so we're going to take, what do we want to use? We'll use R and T in K. Okay, R minus T is in K. Okay, so that's what closure under subtraction is going to mean. If you pick two arbitrary elements in the set, their difference is in the set. So you're going to suppose that R and T are arbitrary elements of K. And then we need to show that R minus T is in K. Okay. Now, the way the set is defined, in order for an element to belong to K, it has to satisfy this condition here. Okay, so this is the condition which defines the set. So in order to show this, you have to show that f of R minus T, in this case, is equal to 0. Okay, so to show this, we need to show f of R minus T is equal to 0. Okay, that's the condition that tells you an element belongs to this set K. Okay, and so now the hypothesis is that R belongs to K and T belongs to K. So both of those elements are going to satisfy this condition. So f of R is going to be 0 and f of T is going to be 0. And then you can use the fact that f is a homomorphism to show that f of R minus T is going to be 0. Okay, so I'll let you finish it off. Okay, and again, it's hopefully this will get you going. So that's SR1, and then you've got to show SR2, the closure under multiplication. And then don't forget to show that it's non-empty. Now, in order to show that it's non-empty, you need to show that there is some element which satisfies this condition, which is guaranteed to satisfy this condition. So, well, the usual thing which is going to satisfy, that's got to belong to any subring, is going to be the 0 element. So to show that this set is non-empty, you basically, and for most subrings, you basically want to show that the 0 element satisfies whatever condition you have here. Okay, so that's what you can do here. Okay, so that's 3. So now let's take a look at 4, because 4 is sort of related to number 3. And so we have that same set for number 4, but you want to prove that f is injective. If and only if K is just the 0 element. Okay, so what we're saying here is that if f is injective, then that set K, the subring that we have in number 3, consists of just the 0 element, just the additive identity element, and then vice versa. Okay, or conversely, I should say. So if K consists of just that 0 element, then f is injective. So this is a biconditional now. Okay, and so we've got backwards and forwards, or forwards and backwards. So our forward direction. So suppose f is injective. And then we need to show that K is equal to this, just the 0 element. Okay, now we always know that the 0 element is in K. So we know that this is a subset of K, okay, since K is a subring. So we need to show, you have to show the other direction. That everything in K is contained in here, which means that the only element in K is 0. Okay, and so you're going to suppose, let's say R is an arbitrary element of K. And then you need to show that R is equal to 0. So you're basically showing that the only element in K is 0. Okay, if you pick just an arbitrary element in K, it's got to be 0. Okay, and so what you're going to use is the hypothesis that f is injective. Okay, so you have to somehow use that hypothesis in order to show this. And you're also supposing that R is in K, so that's going to tell you that f of R is equal to 0. Okay, so that's going to tell you that it satisfies the condition defining K. Okay, but you have to put all this together. Okay, now the other direction. So that's the forward. And then the backward direction. So we're going to suppose that K consists of just 0. And then we need to show that F is injective. Okay, now to show that F is injective, you have to go back to the definition of injective. So this means you need to show for all R and T in R, okay, F of R equals F of T implies R is equal to T. Okay, so that's the definition of injective. So you're going to suppose that R and T are arbitrary elements of R. And then suppose the hypothesis. And then we need to show the conclusion. Okay. So this is setting it up. So now what you've got to work with, so you're supposing R and T are in R, you're supposing this for your hypothesis that F of R is equal to F of T, and you actually don't forget your main hypothesis here, okay, that K is equal to 0 sub R. So what this hypothesis is saying is that the only elements that are mapped to 0 is 0, okay? So the only elements that F maps to 0 is 0. Okay, so you've got to somehow use this hypothesis, use this hypothesis, use this hypothesis to get to here. Okay, so again, I'm not going to continue, okay, but hopefully that'll get you going. Okay, but okay, and let's see, I had sort of, I think I'll skip over 5 and 6. Okay, there was an example very similar to number 5 in the video lecture. And 6, I'll let you puzzle over, but I did want to look at number 7. Okay. So this is to show that the zero factor property is preserved under isomorphism. Okay, and let me actually, this kind of reminds me of something that came up on the homework quite a bit, is that when you're told that something is a ring, that means that it satisfies axioms R1 through R8. You do not know and you cannot assume that it satisfies any of the additional axioms. So R9, the commutativity of multiplication, R10, the existence of a multiplicative identity, R11 is the zero factor property, R12 is existence of multiplicative inverses. So if you're just told that R is a ring, okay, all you know about it then is R1 through R8. Okay, and I know a lot of people on the homework, some of the problems, they were told that it was a ring, or maybe they were told it was a commutative ring, but they wanted to basically use all of the axioms, okay, which kind of makes it a little bit easier sometimes, but it's cheating, okay? So you don't want to do that. So you want to make sure that you're clear on what you can use and what you're assuming about a set. So very often we say, well, we've got a commutative ring with identity. Okay, so that means you've got a multiplicative identity. So that means you have R1 through R8 together with R9, the commutativity of multiplication, and R10, the existence of a multiplicative identity. But you don't necessarily know R11 or R12. Okay, so if you have a commutative ring with identity, then you've got R1 through R10. Okay, but you don't necessarily have R11 or R12. And if you have a field, then you've got everything. Okay, so and we're going to be spending a lot of time with fields in the next chapter, in chapter 4. Okay, but when you're just told that you have a ring, you don't want to assume all of the axioms. Okay. Okay, so let's take a look at 7. Okay, so this is to show that the zero factor property is preserved under isomorphisms. So the importance of an isomorphism is it preserves the arithmetic structure of a ring. And so basically, if you have two rings that are isomorphic to one another, they're essentially the same ring, just using different notation. Okay, I know when I took algebra as an undergraduate, my professor was this, he was this Egyptian, he was from Egypt. Okay, and so he had all these kind of idiosyncratic ways of saying things. And so the way he described it was, well, if you have two rings that are isomorphic, you know, one of them can take the day off and the other ones can show up and nobody will notice the difference. Okay, and that sort of stuck with me. Okay, and so that's basically the idea when you have two rings that are isomorphic, or later on, we're going to be talking about isomorphic groups. It's the same idea. You know, they're essentially the same, it's just different notation. Okay. Okay, so let's take a look at number 7. So this is, so let me just, this is for all rings R and S. If R is isomorphic to S and R satisfies the zero factor property, okay. Then S also satisfies the zero factor property. Okay. Okay, so what we're going to do here is we're going to suppose our hypothesis. So we're going to suppose that R is isomorphic to S and R satisfies the zero factor property. And again, I want to remind you that you need to get in the habit of writing out your hypotheses. Okay, don't, when, you know, whenever you're proving something, you need to actually state what you're assuming. Okay, and it doesn't matter if the hypotheses are sort of there. Okay, because depending on the type of proof you're doing, you know, your hypotheses may not be exactly what the hypotheses are in the statement. If you're doing a proof by contrapositive, then your hypotheses are very different than if you're doing a direct proof. Or if you're doing a proof by contradiction, your hypotheses are going to be different than if you're doing a direct proof. And so you always need to make sure that you state your hypotheses. So here we're doing a direct proof. So I'm just going to suppose the hypotheses as they stand. And so then we need to show the conclusion. So we need to show that S satisfies the zero factor property. Okay, so now you have to look up the zero factor property if you don't remember it. Okay, and so the zero factor property for S now. Okay, so this is for S. So this is going to be, say, for SU in S, for all SU in S. This is if, how do I want to state it? If SU is equal to 0 in S, then S is 0 or U is 0. Okay, so that's the zero factor property for S. Okay, I don't want to state it for R. Okay, so for R, I'd have different elements. I'd have elements in R, and I'd have the zero element in R instead of the zero element in S. So since I'm dealing with S, okay, this is the zero factor property in S, and this is what I want to show. Okay, and so now I'm going to suppose that S and U are arbitrary elements of S. I'm going to suppose the hypothesis here. And then we need to show the conclusion here. So we need to show that S is 0 or U is 0. Okay. Okay, now I'm supposing that R satisfies the zero factor property, so I could have written down the zero factor property in R up here. Okay, the trouble is it gets very confusing. Okay, and so it's kind of better if you don't do that. Okay, up here. Okay, and instead focus your attention on what you're trying to show. Okay, and again, if you took 280 from me, I try to drum this into the students in 280, that you want to focus on what you're trying to show as opposed to what your hypotheses are. Okay, you sort of focus, look forward at what you're trying to show, and then you only look back at your hypotheses when you need to. Okay. Okay, now, so I'm going to go ahead and I'm going to look back at this hypothesis right here, namely that R is isomorphic to S. So R is isomorphic to S. That tells us that there exists an isomorphism. So and I'll just call it F, going from R to S. Okay. So there exists an isomorphism from F from R to S. Okay, and I don't want to go too much further in this proof, but what I'm going to do is I'm going to draw a picture. And I always like drawing these pictures. It kind of helps me visualize what's going on here. Okay. And so F is mapping from R to S. And now I want to somehow, get this involved here. This is what I'm trying to show. So I've got an S and U and S. So I'll go ahead and I'll put those into my picture here. So here's S and U. They're over here in the codomain S. And then you've got to somehow get the fact that R, the other hypothesis that R satisfies the zero factor property involved. Okay. And so what you want to do is you've got these elements in S, you want to somehow get elements in R over here. And then you can apply the fact that R satisfies the zero factor property to these elements in R. And the fact that F is an isomorphism tells you it's injective and surjective, and it's also a homomorphism. But in particular, what we really need is the fact that it's surjective. Okay, so the fact that F is surjective, that's going to tell us that there's going to be some element R that maps into S here. And there's also an element T which maps into U here. Okay, so since F is surjective, there's going to exist these elements over here that map into these elements over here. Okay, and then you want to try to use those elements together with the hypotheses over here. Together with, there's still other hypotheses involved, namely that F is injective and is a homomorphism. So you need to get all of that stuff put together to sort of show what you're trying to show here. Okay, and so I'll let you, I'll stop here. Okay, and hopefully that'll get you started at least.